Hi, this is ET370, Lecture 11, Part B, and here we're going to show you two algorithms that convert decimal to either binary or decimal to hex, and they're very similar, okay? So let's look at this very simple algorithm, and I'm going to give you the steps. Now, the steps are not going to really make sense until we do some example, but let me list them and then apply them. So the idea is you're going to start with the decimal number, and you're going to keep dividing that number and any subsequent answers by the number 2. Why 2? Well, because we're in base 2 binary, right? And you're going to keep track of what's left over, which we call the remainder, right? And you're going to stop when the answer is 0, not the remainder, but the answer is 0, okay? Let's see what happens. Oh, and the last thing is we're going to take that remainder list from last to first, and that actually ends up being the binary number. So let's look at 8 base 10. Okay, and we should know what this is from the last lecture, right? So 8 base 10, I'm going to just tell you is 1, 0, 0, 0, right? And base 2. Okay, and why is it? Because this is the 1's place, the 2's place, the 4's place, the 8's place. Okay, and so we know that 8 base 10 is 1,000. All right, but let's apply this algorithm as if we didn't know this existed and see if we can get the same result. All right, so I take 8 divided by 2. What do I get? 8 divided by 2 is 4, right? Okay, so 8 divided by 2 is 4. What's the remainder? Well, there's nothing left. It's 0. Okay, so now I'm going to take this answer 4, right? Because I'm going to take this subsequent answer divided by 2, and that's 2. And what's the remainder? 0. Now notice I'm still looking. Is the answer 0? No, the answer is 2. Okay, so then I'm going to take this one. 2 divided by 2, what do I get? 2 divided by 2 is 1, remainder 0. Okay, now I'm going to do this. 1 divided by 2, what do I get? I get, well, how many times can 2 fit into 1? It can't. So actually, this is 0. This is my stop condition, right? S-T-O-P, stop. And what's left over? Well, 2 cannot fit into 1, so it's 0 times. So 1 is left over, right? Can you see the remainder list from last to first is 1, 0, 0, 0, base 2. Kind of a neat little algorithm here, okay? And that's what I have written out right there. Okay, let's do another example. Let's do the number 11. So 11 in base 10 or decimal. Let's convert it to binary. So let's follow that same algorithm. So get another piece of paper here. Flip this over. Okay, so 11 divided by 2 is what? I think 5. Remainder, I think there's 1 left over. 5 divided by 2, what is that? 2, remainder 1. Okay, 2 divided by 2 equals 1, remainder 0. 1 divided by 2, oh, we got that nice 1/2 again. We know that's 0, remainder 1. So that means 11 base 10 is from last to first, 1, 0, 1, 1 base 2. And can we check it using our previous tool set? Well, this is the 1's place, the 2's place, the 4's place, and the 8's place. And let's add it up. 8 plus 2 plus 1 is 11. Yay. Okay, this is a neat little algorithm here, right? Okay, so that is that remainder list from last to first. Okay, and I have that just written here. Okay, all right, not too bad. Now, what if we want to convert it to a binary fraction, right? We start with a fraction and we end with a fraction, right? Okay, so it's going to be similar but opposite to decimal to binary non-fraction, right? And so what are we going to do? Instead of dividing by 2, we're going to multiply the fractional part by 2, okay? And we're going to keep track, instead of the remainder, we're going to keep track of the 1's place, and we're going to stop when there's no fractional part left, or the max number of digits it's used. Sometimes there's going to be, I'm going to show you an example where some numbers just cannot be represented perfectly. And we know this all too well in decimal, right? Like what's 1/3? We can't represent 1/3 perfectly. It ends up being 0.333 to forever. It's going to be the same idea with binary. There are just some numbers you cannot represent rationally, okay? All right. Now, in this case, the 1's place from first to last is the binary fraction. So like I said, it's similar but opposite, okay? And I think the way to see it is just with an example. So let's just try it out here. So let's say we have the number 0.625. So we're a decimal fraction and we want to convert it to binary, Okay, and so what do we got to do? We're going to take 0.625 and multiply it by 2. What do we get? We get 1.25. Now we're going to keep track of this ones place, right? And like I said, we're going to stop when there's no fractional part left, or we're just kind of like, we're done with it, right? Okay, let's go to the next one. So I'm going to take this 0.25 over here, and I'm going to, again, multiply it by 2. So what do we get? 0.25 times 2 is 0.5. And I'm keeping track of this ones place. And I'm going to see, is there any fractional part left? There is, so I got to keep going. 0.5 times 2, well, that's 1.0. All right, that's our stop condition. There's nothing left. So now I'm going to look at this first to last. This is my 101. That's going to be my binary number for 0.625, but I got to remember the radix. Remember, that's the radix, the decimal point. So 0.625 is 0.101. Okay, 0.101 base 2. Okay, and can we double check that? We can. Remember, this is the half, quarter, and eighths place, right? And so if we took this, what is it? 1/2 0.5 plus 1/8, right? We're going to get 0.125 here. We add these and we get 0.625. Yes, so this is going to match that. Okay. What about another example? 0.25. Well, actually, I think we should just be able to read that. That looks like just the eighths place. I'm thinking this is going to be just 0.001 right out of the gate, right? Okay, but let's just follow this algorithm blindly and see if we can get the same result that our intuition now should tell us, right? So 0.12, okay, I'm going to multiply it by 2, I'm going to get 0.25. I'm going to take 0.25, multiply by 2 again, I'm going to get 0.5. I'm going to take 0.5, multiply by 2, 1.0. And look at this, the 0 in the fraction, but I'm going to take this 0.001, 0.001, yep. 0.125 is 0.001 in binary. And look at this, half, quarter, eighths, right? This is eighths place, and that's matching that number. Beautiful. So I hope you're seeing that this is a nice way of converting from decimal to fraction. We're going to be talking about floating point arithmetic, and this will actually come back up later, right? But I hope this you can see the utility of this even now. Okay, I want to talk about now an example where some numbers are just irrational. You can't represent it perfectly. And one number that seems pretty exact is 0.7 base 10. So let's try to represent that in binary using this same procedure here. So I'm going to multiply it by 2. I get 1.4. I'm going to take this 0.4. Remember, I'm taking the fractional part and multiplying by 2. I'm getting 0.8. I'm taking this fractional part, 0.8, and I'm multiplying 2 and getting 1.6. Okay, I'm waiting to see, is there any point at which this fractional part goes to 0? Because that's my stop condition. So I can see 0.6 times 2, I get 1.2. Okay, I take 1.2, I take the 0.2, and I multiply it by 2, I get 0.4. I take the 0.4, and I multiply 2, I get the 0.8. I hope you're seeing the problem here. I take the 0.8, multiply 2, I get 1.6. Uh-oh. I get the 0.6, multiply 2, I get 1.2. Can you guys see this is never going to end? Look, the pattern starts repeating, right? What's the next? It's going to be back to 0.4, 0.8, 0.6, 0.2, 0.4, 0.8, 0.6, 0.2. This is never going to end. So at a certain point, you just got to pick, well, how many digits do you want to use, right? How many significant figures do you want to have, and just cut it off, right? So you can see that 0.7 is going to be 1, 0, 1, 1, 0, 1, 1. You're going to just have to like pick a number. Did I get this correct? 1, 0, 1, 1. I apologize. I believe this should be 0, 0, 1, 1. And then so on and so forth, okay? So you must pick a number of bits to end this, right? Okay, let's look at now, how do you convert from decimal to hex? Well, it's gonna be very similar for the non-fractional part. So how do we do this? Instead of dividing by 2, which we did over here, right? When we first did it way back over here, okay? Okay, instead of dividing by 2, we're just going to divide by 16. So if I have 18 base 10, I want to convert to hex. I'm going to divide by 16 and track the remainder. So 18 divided by 16, well, there's 1/16 will fit into 18 and 2 is left over. Okay, I'm going to take this 1 and divide by 16. Well, I can't fit 16 into 1. That's 0, but there's 1 left over. And this is my stop condition, right? Because I've hit 0, right? Stop when the answer is 0. So I'm going to use last to first. That is my hexadecimal number. So 18 base 10 is 1, 2 base 16. And then the question is, can we check that? Does that make sense? Well, let's try it. Okay, so remember, to convert it back, we say 2 times 16 to the 0 plus 1 times 16 to the 1. 2 times 16 to the 0 plus 1 times 16 to the 1. So this is just 2 itself plus 16. Yes, that's 18, because this is the ones place and the 16's place, right? Every digit here is a multiple of 16. Every digit here is just the number. Okay. All right, let's do one last example to end this. And so let's look at 255. We know what 255 should be. It should be FF, right? But let's just double check using our process. So if you take 255 divided by 16, you actually get 15 remainder 15. So if we plug that in your calculator, that's what you would get. Okay. And by the way, 16 by 15 is 240, right? So how many? Yep, 15 is left over. Good. So then we would take 15 divided by 16. Can't fit 16 and 15, so I have 0 with a remainder of 15. Look at this. 15 is my base 16 number, but we know we have to do one more step. 15 is FF, right? We got to do that replacement. And so 255 base 10 is FF base 16. And that's something we already know from the last lecture. Now, it's mentally easier to deal with hex to binary with 4 bits, and we're going to see that in the next part. And dividing by 2 is going to be much easier than dividing by 16, by the way. But I figured I'd show it to you anyways, right? But you're going to see in the next lecture the benefits of how hex and binary play very nicely together. Okay, we'll see you in the third part.